give you instructions on exactly what I want you to do for turning in your project for either the SMAC class or the control class, depending on which one you're registered for. Okay, so what we've done so far is we've hooked up the Arduino and we are looking at system identification. So in the Miller videos, he talks about the formulas for RA, RF, and CT and how that affects the shape of the response when the heater turns on and then the fan kicks on. Okay, so with this curve, when you turn on the heater, the resistor starts to heat up, and then after 100 seconds, the fan kicks on and it cools things down pretty quickly. Okay, so there's two different time constants, one for when the heater is on and one for when the heater is on and the fan is on. All right, so I wanted you to play around with this. This is called system identification, and the goal is to find a good match for RA and RF and CT that Professor Miller had talked about in the videos. So what I'm expecting to see here is a plot similar to this one. Your plot would be different because your room temperature is probably different. And there's some chance that this really wiggles along here and starts to give you a noisy looking plot. If my, for example, air conditioner is on in the house, I don't get a real smooth curve. Like I call this one pretty smooth. So you might want to turn off the AC. You could put your Arduino fan assembly into a box, but what happens there is everything starts to heat up the box, and so your ambient temperature drifts, and you still get kind of wonky results depending on how you set that up. Okay, so this doesn't have to be perfect. This one's a pretty good example of it. If you can get this close, that'd be great. If you're a little bit further from that, that's not a big deal. Okay, so the other thing I want you to do is, essentially what I want you to do is fill out this template, replace my plot with your plot. All right. Okay, the next one, I intentionally chose RA, CT, and RF to be bad in this one. So there's a pretty bad model mismatch, and you can see here, when I turn the heater on, this is way too slow. Even when I turn it off, it's way too slow. The time constant is, I turn the heater on, this is way too slow, right? It's not, the model is the blue line. It's not keeping track with the actual temperature. All right, and then when I turn the fan on, this decays slower than the real temperature. So this system is too slow, okay? All right, so what I'd like you to do is also come up with one that's too fast, at least in the heater on direction, okay? So this one, you see it rises a little bit too fast, and you could argue that's actually not that bad of a match for the fan on portion of it. So I'm just looking for too fast when the heater on condition is true. All right, so paste your own plot in for that. All right, and so eventually I'm going to want a voiceover on these, and I want you to explain, how you chose the values to make these things happen. Did you change CT, and what is the physical explanation of what's going on if you changed CT to make the model either too fast or too slow, and how did you have to adjust RA and RF? Just your line of reasoning, right? It didn't have to be a perfectly rigorous mathematical explanation, just what your line of reasoning was to get to where you had either a good match, too slow, or too fast. Okay, the next thing I want you to do is have your, I forgot the on-off control. All right, so let me insert a slide here. Next thing I want you to do is on-off control, and I'll make a little video on what I'm expecting to see there, but you can do the on-off control, paste your result in to the PowerPoint presentation for on-off control. Okay, so watch for a video for that part. Then I'm also going to have you do proportional control, where you're just manipulating the PID controller for the gain value KP. All right, so I want you to take on different values here. You can barely see that, but it says KP equals 0.25, 0.5, 1, and 2. So you're going to have 4 plots. I'll make a video on how to get those plots. All right, so I'm going to want you to paste those in. And from there, I want you to add some comments. What's going on with the overshoot? What's going on with the settling time? And what's going on with the steady state error? So when you do the voiceover, you need to explain the results you see on this slide. Okay? And what you should see is that there is going to be some steady state error for this condition. All right, so next, the next thing we want to do, we know that to help with steady state error, if we add some integral control, that should help us mitigate steady state error. So I'm going to want you to add in integral control. That means Ki will no longer be 0. So you can experiment with that and see what values of Kp and Ki give you a decent response. All right, so a decent response is one that doesn't overshoot too fast or too much, settles relatively quickly, and achieves a 0 steady state error. Okay, one of the things about this lab experiment is we studied linear systems, but this fan mechanism, because it's got some delay, dead time, if you poke around into the Simulink model, you'll see how that is modeled. It's not a perfect representation of a linear system. It's got some nonlinear elements, so it's not going to match perfectly with the theory, but it is good to see that, all right, and to understand how you can still use linear system theory to help improve the response of your controller. Okay, the next thing I wanted to do is show you the condition where the fan is always on. I'll make a little video for that as well. Fan always on, all right, that is an interesting response because it's closer to a linear system. If the fan is always on, you don't have that dead time business of the fan kicking on and off. So I'll show you an example of that, and I want to see you find controller parameters that exhibit good performance for a set point where the fan is always on. All right, so what you would do here is paste in your result for fan always on, and then add a little voiceover talking about how you tuned your controller for it. Okay, so that's where we're heading. You can just submit this as a PowerPoint with a voiceover, or you could make a screen capture of you talking about it. But that's what I'm expecting to see. Hopefully, it won't take you a long time to do that because you don't have to get this thing tuned up perfectly. Just showing some ideas is what I'm after. Okay, so watch the other videos that explain how to set up some of these things like on-off control, and then I'm going to show you how to set up the MATLAB space to capture plots for different gain values. And then finally, I'll show you a video for the fan always on condition.